From anomaly detection that routes log messages through failure-aware experts, to interpretable text features that can actually be audited, to tokenizers designed by convex optimization rather than heuristic merges, today's papers all ask the same question in different ways. How can AI become more accurate, more efficient, and more trustworthy at the same time? In this episode, we dive into methods that slash labeling costs, sharpen explanations, and even certify how close a tokenizer is to optimal. Let's explore the first paper, FAME Failure-Aware Mixture of Experts for Message-Level Log Anomaly Detection. FAME, or Failure-Aware Mixture of Experts, reframes log anomaly detection from window-level scoring to message-level classification by combining one offline LLM-driven semantic partition with fully on-premise inference. The method parses raw logs with Drain3, samples at most k-labeled lines per event ID, then uses an LLM once to group templates into failure domains. A deterministic certification step keeps only partitions consistent with k-shot evidence. FAME exploits an asymmetric property of rare anomaly sampling. If all k-labels in a domain are anomalous, routing alone is statistically sufficient, while all normal samples still require a classifier. This enables a sparse MOE with a distill BERT gate, a multi-class selector, and per-domain BERT experts, with a special universal normal fallback expert calibrated to catch misrouted anomalies. On BGL, the hardest benchmark because normal and anomalous lines often share templates, FAME reaches F1 equals 98.16 at k equals 100 with 98.18 precision and 98.14 recall using 53,287 labeled lines. A 76 times reduction versus full line level annotation. It also detects 86.3% of anomalies from unseen event IDs. On Thunderbird, where anomalies are structurally separable, it achieves F1 equals 99.95 with perfect recall. Compared with direct in-context LLM classification, which reaches up to F1 equals 96.92 on BGL and incurs $6,698, $10,047 per run for frontier models, FAME costs $10.23 one time and processes up to 1.2 million lines per hour on a single 4-GPU node. Ablations show that a single global BERT collapses to F1 equals 29.65, while removing LLM grouping still leaves a strong TF-IDF variant at F1 equals 93.01, indicating that routed specialization is the main source of gain. Let's explore the second paper, Interpretable Discriminative Text Representations via Agreement and Label Disentanglement. This paper proposes a concrete auditability standard for interpretable text representations. Each coordinate must satisfy conceptual clarity, measured by chance-adjusted inter-rater agreement and label disentanglement, meaning it should not merely paraphrase the target label. The authors instantiate this in LFD, an LLM-assisted feature discovery pipeline that mines contrastive outcome-opposed text pairs, has one LLM-proposed lexical or semantic features, and requires a separate examiner LLM to reproduce the same feature labels before admission. Candidates must clear Cohen's kappa is greater than or equal to 0.7 and add residual held-out predictive gain under a light GBM head. A stylized analysis links the kappa screen to a per-feature annotation noise bound, giving an operating point interpretation for reliability rather than only post-hoc plausibility. Across 10 classification tasks on 7 corpora, including add paraphrase, loan application, CFPB complaints, gaslighting, iSarcasm, December, reviews, and AG News subtasks, LFD matches the predictive performance of the strongest interpretable baseline, TBM, with mean balanced accuracy, 0.708 versus 0.707, while producing materially clearer features. Human audits with 232 raters find LFD features much more reproducible, with human-human kappa around 0.68, 0.69 versus 0.2, 70.45 for TBM concepts, and far less label leakage. Human LLM agreement is also higher, reaching 0.99 on iSarcasm and 0.84 on AG News SciTech. Importantly, LFD achieves this without a post-hoc disentanglement gate, suggesting that cross-LLM agreement plus residual contrastive selection is enough to generate named coordinates that are both predictive and independently auditable. Let's explore the third paper, Tokenization via Convex Relaxations. Tokenization via convex relaxations reframes subword vocabulary construction as a shortest path optimization problem on a tokenization graph, then converts that problem into a large linear program solved with NVIDIA CUOPT PDLP. The resulting method, Convex talk, replaces greedy BPE merges with a global objective over 593,920 climb mix 400B documents and vocabularies from 8K to 256K. The LP relaxation is remarkably tight. Across common vocabulary sizes, the certified gap to optimum is within 1%, and the relaxed solutions become increasingly integral as vocabulary size grows, with over 90% of color variables fixed to 0 or 1 at 128K and 256K. After rounding, the deterministic scheme DET gives the best language model compression, improving bits per byte over BPE on all 1-2 layer models, and usually remaining ahead at deeper settings. For example, at 32K and depth 24, DET reaches 0.7033 BPB versus BPE 0.7042, and at 128K, it reaches 0.6951 versus 0.6968. On intrinsic tokenizer metrics, the bias rounding scheme is strongest overall, consistently improving vocabulary utilization, type token ratio, and tokens per line, while DET is more stable for downstream LM training. The paper's central novelty is not a new merge heuristic, but a certified convex optimization formulation that can quantify how close any tokenizer is to compression optimality on a dataset, turning tokenizer design into a problem with explicit lower bounds rather than heuristic search. That's a wrap on today's AI paper highlights. Thanks for watching.